So we're going to move on now to the next stage of today's session, which is Fourier transforms. I'm not going to go over the detailed maths because this is something that you've done in other classes, but just to remind you that the Fourier transform of a function f of x is defined, as you can see in the first equation. It's an integral from minus infinity to infinity. That gives you the domain of x of f of x times e to the minus ikx. And that gives you the Fourier transform g of k. Notice that we've got a normalizing factor at the front, 1 over root 2 pi. In some definitions you'll find that this is sometimes set to 1, with the inverse transform having a 1 over 2 pi, but that's just convention. That's the formal definition of the infinite domain. As we've said already, we're working with a discrete problem where we have a certain number of points, so we need to define the discrete Fourier transform, which will go over some domain of x from 0 to capital L with n, capital N points. You can see that in the second equation. So you've got capital F subscript little n is then equal to a sum over j equals 0 to n minus 1 of f of x j, so xj being a point. In this case, xj is defined as j times L divided by n. And then you're multiplying that by the exponential of minus 2 pi I j little n over big N. And you can go in the opposite direction. You can do the inverse transform, as shown in the final equation. Little f of xj is given by 1 over capital N. And then you've got a sum from 0 to n minus 1 of capital Fn times the exponential of 2 pi I little nj over capital N. So those are the Fourier transform pairs. That simple implementation of the discrete Fourier transform is extremely inefficient. It scales as the square of the number of points. You'll be implementing this and you should see that. Let's just go pop back to the definition and see why that should be. So if you look at the middle equation there, the second one, capital F subscript little n, you can see that you have a sum from j equals 0 to n minus 1. So that means that for each value of little n, you need to do big N arithmetic operations, and of course there are big N values of little n, so that gives you the n squared. There is an approach, again I won't go into the detailed maths, called a fast Fourier transform, which scales as n log n, which is significantly better, and that is what you will find in almost every scientific and computing application. There are various different implementations. Frequently you'll find that on high-performance computing systems there is a vendor-provided implementation. If you're interested in exploring, there are various extremely efficient packages available out there. NumPy includes a very good version. So you have np.fft.fft, that gives you a one-dimensional Fourier transform. If you want to go to a multi-dimensional one, then you have np.fft.fftn, as shown in the fourth line there. The inverse transform has an I, so you would have np.fft.ifft or iFftn. And if you have real input data, then you can just use the numpy command np.fft.rfft, though you'll have to read that just to be a little bit careful about the indexing and the dimensions. The return transform, as you should realize from the form, the mathematical form will be complex, so you'll be having complex data types, and you have to watch for that when you're plotting. You'll need to plot either the absolute value or either the real or the imaginary. Now, if you've got a Fourier transform of a position x, then the transform will cover wave vectors k. If you're Fourier transforming time measurements, then the transform will be an angular frequency omega. And we'll look at this in a little bit more detail on the next slide, but basically you start at 0, you go up to the domain over 2, and you will wrap back to minus the domain over 2 and back to 0 again. We'll look at that in a second. The spacing in general is 2 pi over the size of the domain, so a big domain gives you a finer spacing. This is the kind of thing that you'll learn more about when you look at solid state physics next year, condensed matter physics, where this kind of transform is extremely important. Let's look at those frequencies and wave vectors. So you can see in the text at the bottom there, it depends on whether you've got an even number of points or an odd number of points. For an even number of points, the first n over 2 coefficients cover the wave vectors from 0 up to k max minus dk. and then the rest of the wave vectors go from minus k max up to minus dk. With the odd wave vectors, with an odd number of points, the coefficients from 0 to n over 2 minus a half. Remember that since n is odd, that's what you would have to do. You have to be a little bit careful if you're doing this with arrays in Python, because Python doesn't like reals, so you'll have to round that to an integer. That goes from 0 to k max, and then the rest of the coefficients go from minus k max to minus dk. You can use that to plot the Fourier transforms if you want to. Notice that functions that are very localized in real space, so something which is very narrow in real space, will be delocalized in Fourier space. In other words, you'll need an awful lot of coefficients to represent it well, and if you've got a function which is delocalized in real space, it will often be localized in Fourier space. In the further work, you'll play with Gaussians for this, and anytime you have a sharp transition, so like a step or a spike, you will find that you get rapid oscillations in Fourier space, and it's very hard to represent a sharp feature accurately with the Fourier transform. And there's a well-known phenomenon called the Gibbs phenomenon, which shows that the Fourier transform of a sharp feature will tend to overshoot. You'll get ringing or oscillation at the edges of the transform. If you think about this problem from a different direction, you can see that we can actually use Fourier transforms to filter. So once you've taken a series of data measurements or a function, you can then remove frequencies or wave vectors above or below a particular value, and that'll allow you to remove noise or to sort of filter out different frequencies. You'll have to think about it a little bit carefully, but that's called spectral analysis, and it's extremely widely used. So I would encourage you to go off and do the exercises now. The first exercise involves writing a function for the discrete Fourier transform. That's the one which is inefficient. If you're struggling to get that to work, I would say don't worry too much about it. It's there mainly so that you can understand how it works. If it's not working, or you're finding it's taking a lot of time, given that we don't have interactive help one-to-one in the lab today, I'd suggest that you just use the NumPy FFT for the rest of the exercises.